Assalamu alaikum. Can you hear my voice? Okay. Sorry for interrupt. Unfortunately, my internet link has some problems. Okay. Today, we want to talk about classification. Firstly, we will introduce some basic concepts, and then we will continue and with some famous and major classification techniques in this part. And finally, in this chapter, we will talk about some measures, some metrics to calculate performance of all classifiers. Okay, as we talked in chapter 1, when we are talking about learning, machine learning, we have two different groups of machine learnings. One of them is supervised learning and the other is unsupervised. When we are talking about supervised learning, it means that I have a supervisor. This supervisor helps me during the training phase. I have a training phase. During this phase, a supervisor helps me to learn about the data, about the environment around my data, space of my data. Okay? This supervisor can help me improving the learning process. Can you see the slides? My slides, the uploaded slides? Okay. So Muhammad Hassan, please left the class and enter again if you cannot see the slides. Okay, so in supervised learning, the supervisor helps me to improve my learning process. And then during a test phase, I can answer more clearly with more accuracy. Why? Because I learn in the training phase according to the the supervisor's help. One more note is here. One more note. This supervisor can shape my mind how I should classify the data. The supervisor will shape my mind, my learning process. Okay. On the other hand, we have another type of learning. It's unsupervised learning. In this type of learning, we have not a supervisor during the learning process. What does it mean? It means that I should learn myself based on my understanding from the data. Maybe my understand, maybe my understand is true, and maybe it's not true. I don't know, because there is no metric or measure or supervisor who helps me during this learning. I should think about something according to the data mining process, the data or my data mining goal. As I repeated it multiple times during this course. During a data mining process, I have a goal. And when I'm using unsupervised learning, it means that according to that goal, I should create a metric for myself to learn. I have some data, I'm watching them, and I should learn. But how? I don't know. Just I should think about the goal and create a knowledge about those data. There is no pre-knowledge about those data. So it's my own opinion or so this type of learning is clustering. So in clustering, I should find a metric and I should work to learn myself. In this chapter, we will talk about classification, and in chapter 10, we learn more about clustering process. But if you watch my videos about using pre-processing steps in VECA, when I used filters in VECA, in the tree you can see that there are two different types of filters. One of them is supervised filters and the other is unsupervised. They are related to our content. So in this chapter, we only focus on the classification. As I said, in classification, I have a supervisor. This supervisor are not something special. It's not an object or an entity. My supervisor in classification is not an entity or an object. These supervisors is a set of records in my data set. These records have labels, class labels. So I know their types or I know their class. In classification, my goal is determining the class label of a record. And now I have a supervisor. I have a set of records. These records have class labels. So I can learn about those labels, those classes, according to this set. During the training phase, I'm working on this set, a set of records with class label. So my goal is to predict the class label of records. This class label maybe is a discrete data type, or maybe it's a nominal data type. And during the classification, I should use a classification process, a classification method, algorithm, to construct a classifier according to those training data, to those data with noun class labels. And then using that classifier, the classifier that I build it during the training phase. In the training phase, I create classifiers. And then in the test phase, I'm using that classifier to classify and to predict the class labels of the other records. I'm repeating again. Most of the time, my class labels is a discrete numeric value, or is a nominal value. Using a continuous data type is not good for classification. I can do that. I can select, I can create a classifier to predict continuous values. I can create, but its result may not be good. So it's better for me, it's better to use a discrete value or a nominal value for class labels. I can change them easily into together. I can change a discrete value into nominal, or assigning a value to each nominal label. So my goal is predicting those labels. And as I said, I can use numerical continuous value for class labels. I can use them when it's good. For example, in pre-processing, we talked about finding some missing values and putting a value for those features in the records which they are they are empty, they have no values. So using a classifier, I can predict some values for those empty features, for those unknown features with unknown values. So I can use classification to predict this type of these missing values. We can use classification in different applications. For example, a bank can use a classifier to classify its customers. For example, I'm asking my bank for a loan. The bank can qualify me using a classifier. They can create a classifier and they can qualify my behavior, my bank account behavior. And then they can create a credit for me, or they can refuse to give a loan to me. For medical science, it's common today that we can use classifiers to create a medical diagnosis system, especially for diagnosing cancer or something like that, different type of cancers, lung, breast, and different types of cancers. We can create a classifier to diagnose them. For example, I have an X-ray picture, and I can give it to the classifier, and it can say, the classifier can say, okay, this is a cancer or no. Is this a tumor or no? Is this tumor is benign or no? Yes or no? Sometimes I'm trying to detect some frauds, especially in financial systems, such as banks, or in computer networks. We can use fraud detection systems. And the heart of those fraud detection systems can use classifiers. For example, in a financial system, a classifier can say that this transaction is okay, yes or no, or it's a fraudulent transaction. To categorizing web pages, search engines are using classifiers. We can use classifiers in different types of applications. You can find too many applications who are using classifiers. Okay, so according to our knowledge until now, I can say that the classification is a two-step process. The first step is creating or constructing a model or a classifier according to the training data. As I said, my training data is a set of records who have class labels. So firstly, I should create a model, a classifier, according to those training data. And here I'm using the supervisor, because during this constructing this model, I can use the help of those defined class labels, predefined class labels. So I can create my model based on a pre-knowledge in my training data. After creating this model, in the second model, in the second step, I should use this model. How? I have a classifier, and I'm putting new data, a new record to the classifier, and the classifier will predict the class label of that record. I'm inputting the data into classifier, and it will say to me the class label is blah blah, or is something X, Y, or something else. I don't know. One main question is arised here. How can I find that this prediction, the return result of the model, is correct? Maybe my prediction is correct, maybe it's incorrect, I don't know. But how can I measure accuracy of this model? So I need to create some measures or define some measures to estimate the accuracy of my model. Maybe I can create, we will learn in this course that we can create different classifiers using different classification algorithms, okay? And then I should find the best classifiers among them. So I have to estimate their accuracy to select the best model. To do this, I should test my model. How? I have some records with noun labels. I'm hiding the label and inputting the rest of data of that feature to the classifier. The classifier will return its prediction to me, and I can compare the prediction with the real class label. During the test phase, I know the class label. Just I'm putting the data of that record to the classifier. The classifier will predict the class label, and then I should compare the classifier's result, the result of classifier, with the real class label, and then I can say that the prediction is correct or incorrect. We define the accuracy measure. Accuracy, we define that accuracy is a percentage of cases that the classifier predict correctly among different test samples. How many of those predictions are correct? I should find a percentage about the correct results. One main note that my test set should be different, must be different from my training set. I'm learning according to training set, and for the test set, I should use another set of data. Otherwise, if I select some data, some test data from my training data, my model will be overfitted. We have two problems in creating models in data mining and in machine learning. During machine learning, we have two main problems. One of them is underfitting, the other is overfitting. During the underfitting means that I have not enough data to train my model. So the training phase of my model is not completed. This is underfitting. So my model cannot predict correctly most of times. Its accuracy will be low. The second problem is overfitting. Overfitting means that I learn my model with too many samples. Think about a student, a child. He or she learns, for example, learns some basics in mathematics. For example, learning add or subtracting, adding or subtracting. If I give him or her lots of examples, his mind will be shaped according to those samples. From a noun point, if I continue using those samples, we can see that the performance of that student will decreases. Why? Because he or she overfits. After a point, if I continue my process, my learning process, we can see that the learning performance will decrease. And for training set and classification, if we do something like this, our model will be overfitted, and then the performance of my model will be decreased. So we should be aware about the overfitting and underfitting during the training phase. We should be clear about that. We will talk about these problems at the end of this chapter. Okay, so until now, I'm creating a model, a classifier model, to predict class labels in some records in my data set. And if the accuracy of this model is acceptable, So I can use my model. My model is, my classifier is good and accept it, and it will be accepted to do my application. Sometimes instead of saying test set, we are some people say validation set. Validation set is test set. Okay, so firstly, I have a data set in my training set, and according to this training data, I'm using a classification algorithm to create a classifier model. This classifier model will predict the class label of the record in my dataset. This is the first step of classification, and the second step is this. I have my classifiers and I have some testing data or a test set. I'm applying the classifier on this test set to find the accuracy of my classifier, to test the accuracy of my classifier. If it's good and the accuracy is acceptable, then I can use my classifier in the real world. Please note that in the real world, the model will see new data or unseen data. Unseen data means that these data are not presented in my data set. They are new. They don't repeat it in my data set. So I'm saying unseen data, the data that I didn't see them before. And now, in reality, I can talk about the performance of my classifiers. Most of times, my classifier has some performances in the lab during the training and the test. Okay, but in reality, when I'm using the classifier in an application, in a real environment, we can see that the performance of my classifier decreases. Why? When something like this happens, it means that my model is not completed. There are some data entering into the classifier. These data are new, and my classifier does not see them before. So its performance will reduce. Because in the structure of the classifier, there is no predefined structure or rule or something like that to find the class label of that unseen record. So it must say something randomly as the class label. For example, in the USA, in the hospitals, there are some applications, machine applications, who are diagnosing sickness or illness of patients. The patient goes to the hospital, to hospitals, and say, "I'm sick." Okay, he or she goes and they give some tests from him or her, and then an intelligent machine would predict his illness or his sickness. In a few years ago, and then the doctor will say that, okay, use these drugs, for example, or something like that. So the machine will predict the illness or sickness of the patient. A few years ago, one of those intelligent machines predicts the result with low accuracy. And after analyzing the data and the classifier structure of that machine, they found that the structure of classifiers is not good when some new unseen data enters into the classifier. It means that their classifier should be trained again to train and to learn the new states of the patients. So we should know that our classifier may have good accuracy at this time, and maybe during the time its performance decreases because of unseen data, and at that time we should create the classifier model again. We should train it with new data during the time we are capturing data. So we can train the classifier with those new data in the future. Okay. Now we learn some basics about the classifications. Let me talk about some of those classifiers. Be familiar with some of those main classifiers. The tree induction or decision tree classifiers, standing among the best classifiers, the most we can understand their structures easily, and also their performance is good in most of cases. So in this part, we will start with decision tree classifiers. For example, I have this data set. This data set has 5 different features: age, income, student, credit rating, and buying computer. Buys computer is my class label. This class label show me that a customer buys a computer or no. So we can see that buys computer feature is a nominal feature with 2 different labels: yes or yes and no. Also, here we can see that income, student, and credit ratings are nominal too, and the age feature is a discrete feature, discrete type feature. The age is discreted into 3 different parts, or 3 different values. One of them is less than 3, less than 30. One of them is a value between 31 to 50 to 40, and the last one is greater than 40. It's about the age. We discrete the age of our customers into 3 different categories. One of them is customers with age less than 30 years. One of them is customers with age between 31 to 40 years. And the last category is customers with 40 years age. Okay. Also, for income, we have 3 different categories: medium, low, and high. For students, some of my customers are students, some of them are not, and their credit rating are fair or excellent. According to this data, I want to create a model to predict that when a new customer arriving to my store, I should predict that he or she will buy a computer, yes or no. So my goal is to predict that a new customer will buy a computer or no, according to this data. And here you can see the decision tree result, the decision tree. We will talk about this tree, how we can create this tree. We will talk about it. But currently, we just want, we just have a look on this table. Here, you can see that, firstly, I want to predict that he or she, a customer, will buy a computer or no. Firstly, we should talk about their ages. If their ages is a value between 31 to 40, the customer will buy a computer. Its class label yes, is yes. But if the customer has age less than 30 years, we should know that is the customer a student, yes or no? Is he a student? Credit rating. If they have a fair credit rating, so they will buy a computer. To find a good example for class, if please read page
credit rating is excellent
of the book.
They won't buy a computer.
Of a textbook.
So you can see the structure of this tree is completely clear.
There's a good example. Computer.
For ages higher than or greater than 40 years, we should talk about or ask about their credit rating. If they have a fair credit rating, so they will buy a computer. But if their credit rating is excellent, then they won't buy a computer. So you can see the structure of this tree is completely clear. This is a classifier model. We create it according to the decision tree algorithms. But here, this is an ID tree, decision tree classifier. Sansan say that the following decision tree is for the concept by computer that indicate whether a customer, the company likes to buy a computer or not. Each internal node represent test. Each leaf node represent. Yes, Mohammed. Yes, Mohammed Hassan. Mohammed Hassan creates an abstraction about this tree. Okay, so here this tree is created based on ID tree algorithm. We have different types of decision tree. Please note, we have different types of decision tree. This tree is created based on ID tree algorithm. So to create this tree, this decision tree, we can use a greedy algorithm. We are starting from the top. And in a recursive manner, just we use a divide and conquer strategy to create this tree structure. At each level, we have a set of attributes. We should test those attributes according to the class label or to the category. We should test different attributes and their relations, finding the relation between attributes with the class label or with the category of those data. And hence, For each part of the tree, at each level, we are selecting that attribute who prepare the best decision for me. It means that at each level, at each part of the tree, I'm selecting an attribute with the highest information gain. With the highest information gain. So I should define the information gain. This process will be continued until a stopping criteria. But what is the stopping criteria? The process will stop when I'm classifying all the whole data, finding this, and I'm seeing that the data at, let's suppose that I am in a specific part of the tree. I am in a specific part of the tree. So the question is this: should I continue to creating some new childs, a new level in this part? Yes or no? In this part, I'm in a specific part of the tree, and the question is this: should I continue to construct the tree in this section, in this part? Yes or no? We will stop the process if the samples at that part, all of those samples at that part belongs to one class. For example, here in this, look at this. When I'm talking about the age, I say that the customers in the range with the age between 31 to 40, all of them will buy the computer. So I stop the process. Why? Because all of the samples in this part, in this specific part of the tree, belongs to the same class, to one class. But for example, for ages less than 30 or higher than 40, we can see that this criteria is not happened. So I will stop Sony is cutting. I'm repeating again. I will stop the creation process in a specific part of the tree when all samples at that part belongs to the same class. The second condition that I can stop the process, the creation process, is that there is no feature. There is no feature that I can use to create a new decision. Starting from the top, from the root of the tree. At each level, if I follow a path from the root to the leaf. At each level, I'm using one of the features in the dataset. For example, in the past sample, at the first time, I'm using the feature age. And then I'm using the feature, for example, a student or credit rate and something like that. At each level, I'm using one of those attributes. So the remaining attributes or features will reduce at each level because I'm removing one of those attributes. I'm selecting one of those attributes and removing it from the set, the remaining set, one by one. And finally, for example, if I have n different features, finally, after n levels, there is no feature to make a new decision. So the process will be stopped because I'm using all the features at level n. I'm using all those n features. At this time, I should make the decision. How? I'm using the majority voting. I should define the class label at that time, and I'm counting the remaining samples at that level, at that place, at that point in the tree. I'm counting the at that place, at that point in the tree. I'm counting the samples belongs to each of those classes. And then I'm saying that, for example, the class label X has higher number of samples here. So simply, I'm saying that the class label at that leaf is X. Why? Because its follower at that place, its follower, number of followers at that place is higher than the number of followers of the other classes. It's a majority voting. And the third condition to stop the partitioning, creating the decision tree, is when there are no sample left. I'm testing all the conditions and all of samples are defined their positions in the tree. So at that time I can stop the process. Okay, so until now we learned about the classification and creating the model. We learned that to create the decision tree, we should find at each level, at each places in the tree, I should find the best attribute at that level, at that place. I should find the best attribute to create a new partition. So the main question is this: what is the best attribute? We say that that attribute should have must have the best information gain for me. So what is the information gain? I should define a metric, a measure for this. Here, I'm preparing a review for entropy. Entropy is defined in information theory course. Entropy is a measure of uncertainty. It's associated with a random variable. To calculate the entropy, I can use this formula, sigma I minus of sigma I from 1 to m of pi log of pi times in log of pi. I can use this formula to calculate the entropy. But look at this plot here in the bottom of this slide. Let's suppose that I have a class with two different members. My class labels has two different labels. Okay, it's the most simplest case. My model is a two classes model. Its class label has only two different values. Okay. I want to define the probability of X, item X. I know that the probability of item X, when I want to define that X is belonging to the, for example, to the first class or to the second class. The probability of belonging X to the first class is something, and belonging to the second class is something else. I know that when X is completely belongs to one of those classes, I can certainly completely can say that X is belongs to, for example, to class 1 or to class 2. When X is completely belongs to a predefined, there is no doubt, there is no uncertainty. Completely, I can say that X is belongs to that class. For example, all of you are from Iraq, okay? So you are belongs to the Iraq category. There is no doubt. There is no uncertainty in this. Okay? For example, all of us are living in Asia. So we are in category Asia. We are not in the Europe. There is no doubt, there is no uncertainty in this case. So when there is no uncertainty, we can say that the entropy is 0. But for example, I'm visiting someone and I'm not sure about the nationality of that person. For example, a person in the West with the nationality of, for example, France, Germany, or something like that. But I know that his parents, his ancients, are from, for example, Iraq or Iran. And now at this time, is that person a German person or a French person, or he's an, for example, he's an Iranian person or Iraqi person? Which of them is correct? He is from Germany or from Iraq? I don't know. Here I can see there is an uncertainty in my speaks, in my sentences. I don't know he or she is from Germany or Iraq or Iran. I don't know. At this time, I'm saying, okay, you are from Germany with 50%, and you are from, for example, Iraq or Iran with another 50%. It's a 50-50. Your parents, your ancients are from Iran or Iraq, and now you and your children are in Germany. So in this case, I can see that there is an uncertainty here. When I'm saying 50-50, I have the maximum uncertainty. So the entropy is 1. This plot shows the values for entropy for different cases with different probabilities. I know that the probability is something between 0 to 1. And also the entropy is between 0 to 1, 2. Also, I can define a conditional entropy, h of y with condition x can be calculated using this formula here. It's a conditional probability. And again, I'm saying that I should mention that here in this slide, I'm talking about a case, a class with 2 labels, a case with 2 different classes. In reality, most of times we have more than 2 classes. For example, when I'm testing someone in medical diagnosis, I'm testing someone and I'm saying, okay, you have COVID-19, yes or no? This is 2 class values, yes or no? But for example, when I'm talking about the type of illness, maybe someone is ill, sick, and I should predict the type of illness. Okay, that illness may be a flu, a kind of cold, a cancer, a headache, I don't know. There are different illness. So different else. So my class has more than 2 labels in that case. Okay. We talked about ID3, so we should talk about its attribute selection measure. The attribute selection measure in ID3 is information gained. So we should define the information gain, because we said that, okay, we are selecting an attribute with the highest information gain in each level and each part for partitioning. Let's suppose that P of I is the probability of probability that a tuple, an attribute, arbitrary tuple, a random tuple. Okay, I'm selecting a random tuple. I'm saying that the P of I is the probability that the tuple in dataset D belongs to the class C of I, Ci. So this probability is calculated using this number of records belongs to the class I divided by the number of records in the dataset, D. This is the probability that a record or a tuple belongs to a predefined class. Okay. And now I'm defining expected information or expected entropy for a tuple in dataset D using this formula. You can see this formula is entropy formula. And also, we are defining a new measure, information needed to classifying D. I'm using attribute A to partition the tree into V different partitions. For example, I want to split the tree into V different partitions using attribute A. So I should use this formula to calculate the information of that attribute when I'm trying to partition the data set according to that attribute into V different partitions. And finally, I'm defining the information gained of attribute A using this equation, information of D minus into information of D when I'm choosing attribute A. This is the formula to find a measure. I want to choose attribute A. Is this the best attribute for partitioning, yes or no? We should define its gain, calculate its gain to do this. Let's have an example here before ending the class. We have an example here. We in the past example we had this data set. This data set has 2 different classes: the class positive or P or with label yes, and the class negative or with label no. Okay. If I count number of yes and no, or number of positive and I know, Nuradna, I know. I'm finishing it just in a few minutes. Just wait for a few minutes, I will finish it. Counting this number of records belong to these classes, class positive or negative, I can see that in 5 tuples belongs to class negative or no, and 9 other tuples are belong to the class positive or yes. So information of D, of dataset D, is information of 9 and 5. I'm using the formula and I can see that information of D is 0.940. For example, here, I want to find the best attribute for partitioning. I have different partition, age, different features, age, income, student, and credit rating. And the question is this: which of them is better than the rest? Which of them is the best? Here, I'm calculating the information gain for attribute age. When I'm selecting attribute age, I can see that putting data in the formula in the last slide here. Here, I'm selecting attribute age. I want to define its information gain. Information of age is calculated in this way, and finally I can see that information age is 0.694. Okay, and this information of age and information gain of age is information D minus 2 information age is 0.246. I can repeat this calculation for the rest of these attributes for income, student, and credit rating. I'm calculating and find this result. Gain of income is 0.029. Gain of students is 0.151, and gain of credit rating is 0.048. Now I can see that the attribute age has the highest information gain. So at the root, I'm using age attribute to partition the data. The age attribute has 3 different partitions. Here you can see those partitions, 3 different partitions. Income has 3 partitions, a student has 2 partitions, and credit rating has 2 partitions. Please, until the next week, please calculate all of these values for the rest of features. As a homework, please calculate the gain information for the whole tree. This is the whole tree. Prove for me that this tree is correct. Prove it for me as a homework. I will assign a homework. I will upload a homework for you. Prove that this structure is correct. The first step is here. Just repeat this and show me that this structure is correct. Okay. Okay. Thank you for joining the class. Have you any question? Okay. Thank you. Happy Eid al-Fitr. I don't know. In Arabic, what do you say to Eid al-Fitr? In Arabic, I don't know. But Happy Fitr. I wish the best for you, Eid al-Fitr. Okay, thank you, Muhammad Hassan. Happy Eid al-Fitr. I wish the best for you and your family in this Eid. Thank you and bye.